Welcome to the Daxbot podcast, episode number 3. Me, Jason Richards, and Jonathan VanSchenk.
That's me. Thanks for having me on.
Man, you bet. So, Jonathan, tell me about how in the world did you get involved with Daxbot? What's your background? Are you from Oregon? All those things.
Yeah, for sure. Well, let me just start out. So I am the head of engineering here at Daxbot, and I joined on the company, I think it was last September, if I remember correctly. So this is about a year and a half for me or so that I've been working here. And I started on as a intern doing software development here, and then kind of over the course of working became a full-time employee, and now I sort of help lead the engineering team. Which is it's a little funny that I'm a fairly new employee, being lead of engineering, but I think that sort of speaks more to the engineering team does a lot to lead themselves. So most of my responsibilities have to do with just sort of making sure people know what's important for them to be working on. But the team here definitely runs themselves for the most part, which is pretty great. Yeah, so the engineering team mostly runs itself, and it's definitely a dream to get to work with them. But the way that I actually got involved with Daxbot is I did not study software engineering or anything. I actually don't have much of a background in it until I sort of have been doing it for the company here. I actually got my start in academia. So I was in a PhD program at Oregon State University studying physics, which was quite a party. I really, really loved the field. But as I was getting to the end of my PhD, kind of like wrapping up a lot of the aspects of my research there in the lab that I was doing, I was kind of realizing, I'm like, oh, well, I'm not sure I really want to do the professional researcher thing. Just the lifestyle that kind of comes along with being a professional researcher entails lots of working on weekends and after hours, and it's a pretty big slog until you've kind of established yourself in the field, and so for people who like really love research, it's worth it. But as I was getting near the end, I realized, like, well, I'm not sure it's really worth it to me to kind of put another 10 years of my life into really breaking my back to make this happen. And so I started kind of looking for other opportunities, and I spent some time thinking about, like, well, what is it that I really enjoy doing? And kind of what I came to is, it's like, well, I really love getting to work with my coworkers and develop like software tooling to kind of solve the research and experimental problems that they're having kind of in the research lab.
Sure.
Yeah, and I was spending time thinking, like, well, I mean, that sounds an awful lot like being a software engineer. And so in the last year of my PhD, I spent a lot of time really developing my skill set and kind of developing my portfolio as to pivot to start doing software engineering instead of physics research. And then as I was getting near the end of my program, I applied to work here at Daxbot, and fortunately you all hired me, and so I've been working here since then.
Nice. Well, that's awesome. So it's funny too. I mean, the stuff that we want to talk about today is, Dax's invisible rails, and obviously there's a lot of math that goes behind that, and physics and things like that. We were joking before we started that I was like, that has to do with like circumference, right? And it was like, okay, you can't ask those kind of questions.
Yeah. It's been very fortunate. I think that a lot of the projects that I've gotten to work on here at Daxbot, I have used a great deal of what I learned in my PhD. I had the opportunity to study a lot of kind of pretty heavy lifting math and physics concepts.
Sure.
And I've really been able to kind of bring that to bear here at the company. And so it's been fun that I've been able to use my PhD and kind of the research that I did there, as part of this company, even if it is not, strictly the same kind of thing. But yeah, what I really love getting to do is kind of dig into the really complicated, knotty problems and, figure out how we can, develop good tools and, math models and stuff like that. And I'm sure we'll get into that in just a second here. But.
That's kind of where I was hoping we'd go right now anyway, because when you look at the problems of, so for example, Sean showed me a video last week about Dax, from the Dax POV, the Dax point of view, driving down a sidewalk by himself autonomously on the invisible rail system, these white arrows that change colors as he's going through different like difficulties.
Yeah, for sure.
All the things that go to it. When I watch it, I'm amazed, just as a more of like an outside perspective, right? I just watch this robot and he just goes down the path by himself and he's able to navigate intelligently around different things. That's amazing. So that doesn't just happen though. I mean, right? That's the thing that I love is talking to a lot of people in the business world, and in most people's minds, like the movies, right? Like in science fiction, robots are just magic, right? They don't understand that there's a lot of things that go into it. So when they see Dax rolling down the street, to them it's just magic. And they're just like, oh yeah, of course robots can travel this path by themselves. But for people that are engineers, they understand, wait, there's a lot more that goes into that, right?
Yeah, and a little bit of magic.
A little bit of magic, but yeah. So tell me about that. Like how do those pieces come together in such a way that it looks seamless and it looks like magic to the outside observer?
For sure. Yeah, no, for sure. And maybe we'll get a little bit of an insert here for if there are people watching the podcast that they can see kind of the what you're describing right there. But sort of the idea is if you want a delivery robot, which, that's kind of the main task that Dax is trying to accomplish these days is doing kind of last mile delivery. There's a lot that goes into how you actually get the robot to get from point A to point B. And I guess I'd say, first of all, if you think about the way that you as a human go about navigating sidewalks or, walking through, there is kind of a lot that happens sort of subconsciously in your brain where you're not like actively thinking about the pieces of it just in your brain you have this notion of what sidewalks are and sure. You can and you can just like look at a chunk of ground inside of your city and immediately tell like, oh, this is a sidewalk, that's a median over there, that's grass, and so you just know pretty intuitively where you're supposed to walk and where you're not supposed to walk. But if you stop and think about it for a second of how would you actually describe to somebody what a sidewalk is? So, say you've got an alien that, comes down and, visits your city, and you're trying to tell this alien, oh yeah, make sure you walk on the sidewalks, to get from point A to point B. How do you actually, articulate to them all of the details of what that really entails? And, and it's really challenging. It's really, really hard to figure out in a way that kind of encompasses all of the edge cases, how you describe what a sidewalk is. And so one of the ways that we were kind of solving that problem for a while was we were actually using neural networks as a way of trying to classify sidewalks. So you'd use the cameras on the robot, and the robot would so Dax would essentially have a photo from the perspective of his camera of the space in front of him. And then we would take that photo and run it through a neural network that we've sort of trained on images like this, and then it would go through and basically layer on top of that image a classification map. So it basically would paint on the image like this is all of the places on this image that correspond to sidewalk, and then these are all of the parts of the image that correspond to driveway or grass or things like that. And so kind of what we get out of that sort of machine learning algorithm is a way that we can kind of convert the pixels of the image into the idea of what those pixels are actually representing. And then from there, you can then start to begin to do things of like, okay, now I know, from the cameras of the robot where the sidewalk is. Now I can start to do things like, okay, if I know that there's the sidewalk that's going in front of me and I'm trying to go in that direction, is the sidewalk wide enough for me to actually safely traverse it? You can kind of start to do those pieces. But kind of the reason why I go on this little diversion here is to sort of articulate the idea that actually navigating through situations is like really, really challenging. And as humans, it's kind of deceptively simple, but that's only because we've been doing tasks like walking on sidewalks for basically our entire lives.
Sure. It's kind of like I joke with people all the time that anytime you do something for the first time, you stink at it. I mean, right? I mean, I have little kids, you have little kids, and so teaching them to walk, it's pretty simple once you get the hang of it.
Right.
But getting to that point, so I guess in the same way, like having a robot learn is going to be tough.
Right. Or, in the case of like toddlers, it's like, my son is still learning how to identify what sidewalks are and what sidewalks aren't.
Scraped knees.
Yeah, totally. And so the idea of actually being able to have the robot navigate is kind of really this pretty complicated question. And even that small piece that I was talking about before of being able to classify, aspects of an image as this is sidewalk, this is not sidewalk, that doesn't then begin to take into account the other kinds of considerations of, like, how does the robot actually know where it's trying to get to? Given that the robot, like, has this image of what's in front of it, is that actually pointed in the direction that the robot wants to go? And then you have this image that you've then done processing. But what happens if like a dog jumps in front of the robot immediately? Like that was sidewalk before, but now it's actually like furry canine, and so it's not safe to drive there anymore.
Yeah.
And so there's lots of questions like that end up making this task of how do you actually have a robot navigate safely on sidewalks actually pretty challenging.
Sure. So when you pose it to me in that way, and I have a little bit of background in software development, so my brain starts thinking of how to do it, but it seems overwhelming. So what was your journey of going from, okay, here's the big overwhelming problem, and you put it into bite-sized pieces, but what were those bite-sized pieces, and what was your journey of going from, here's the big problem, to what is the first thing that I need to work on, and basically to where we are today?
Right. Yeah. Well. I'll actually put it back to you for a second because I want to pick your brain about this, and that is, say we're wanting to walk down to the coffee shop to get another cup of coffee after this.
Cheers.
And so I tell you, like, how is it that you would actually execute on the task, walk to the coffee shop from here? Kind of what are the things that are sort of going through your mind as you're thinking about executing on that task?
I think it's just, what is the next thing in front of me? Meaning, I think the first thing that comes to mind is get back, stand up from the chair, walk to the door, open the door, close the door, walk down the stairs, open the door, get to the sidewalk, start going down the sidewalk, get to the crosswalk, look both ways, don't get hit by a car.
Totally.
Frogger, right? And eventually get to the coffee shop, order the coffee. So, is that what you mean?
No. That's great.
Okay.
I wasn't fishing for anything in particular.
Okay.
I was just really curious what you were saying.
From academia, I'm just making sure I get an A on this assignment, Professor.
Yeah, totally. And so what I sort of hear you articulating there is if you can split the task up into a series of kind of much smaller, more bite-sized and manageable pieces, then maybe this task is actually, accomplishable, where the notion of like just walk to the coffee shop isn't maybe tractable to begin with, but you sort of split it up in your mind of like, I have this sense of, sidewalks and I'd sort of maybe put in a little bit of maybe what was going on even more subconsciously for you is you sort of know where all of the sidewalks in Philomath go. And so if you were thinking about how to get to the coffee shop, one of the first tasks is, well, how do I actually figure out the route that I'm going to take to get there? And you're thinking through, well, okay, yeah, but I know there's construction on 14th, and so I like that sidewalk's closed or something, or but the shoulder's pretty wide, so maybe I could just like walk around the ditch witch that's on the side of the street or something like that. And so there's this pretty sophisticated and high-level routing thing that your brain does first of all, of how do I like imagine the way that I get to the coffee shop, and then you split that up into a series of tasks. And so the first one is like stand up and get to the door, right? And so that's really the first step in figuring out how to have Dax go from point A to point B, and is can I use basically my background knowledge of the city that we're in to kind of plot roughly how to get from point A to point B and split up the task of navigation into smaller pieces. And so this is, the way that I think about it is this is the long time scale problem of where are the sidewalks in the city, which of them are safe to navigate on, where do they actually go? And for all of that information, we can just like stick that in a database because it doesn't really change all that frequently.
Yeah, sure.
So, we could go through the whole city to begin with and figure out like this is the latitude and longitude values of all of the places on the sidewalk, and this is how wide they are, and this is what surface type they are. This one's really rough, that one's really smooth, and kind of answer all of those questions for the way that the city is just kind of on your long time scale average. And once you do that, that's actually like a huge part of solving the problem is getting that kind of background information. And I would say that this is, again, sort of roughly akin to the way that you as a human rely on your like past knowledge of actually navigating, because there's a lot of other pieces to it, right? Where you also happen to know maybe some sidewalks are in good condition and some sidewalks are in bad condition, or like, Frank, he never trims his hedge, and so I don't really like walking down that path because I gotta inch to the side, and so there's a ton of like localized knowledge that's just sort of floating around the back of your head, and we can bring that to bear by just making a query from a database to pull like what are the good sidewalks? And all of that can just happen on a server somewhere. So if the robot's like, I want to get from point A to point B, there's a ton of things that we can just say, hey, web server in the sky that knows about my city, like, how would I roughly get from point A to point B? And then it can respond and say, these are your 10 sidewalks that you're going to walk on. And it could even give you latitude, longitude, altitude values for all of them. And again, information about surface type of, things like that. And so we can do most of the routing just kind of completely off bot and, have the robot not need to know anything about that. And so for the robot actually navigating, you can boil the task down to, how do I get the robot to follow a predefined path in an intelligent way?
Yeah.
So we do all of the routing kind of like off the robot, and then all that the robot sees is it's like, I've been told that I'm trying to get from point A to point B.
Yeah.
And then the magical server in the sky tells me that, this is the, points, set of latitude and longitude values that I actually want to follow. And if I do that, the server promises me that I will get to the place where I'm trying to go.
Yeah. That makes a lot of sense. From even a human element, I lived in Seattle for about 4 years, and Google Maps became my lifeline, right? It was I have no idea where I am, and I have no idea where I'm going. Please help me.
Yes, yeah.
I know how to navigate a car, right?
Totally.
And I know where I am,
mm-hmm.
roughly, right?
Yeah.
Because it's kind of like you are here. How does a robot do that? In the sense that, the accuracy that we have to have for that, when you're talking sidewalks, when we're talking an interstate and you've got multiple lanes, you can drift a bit and you're going to be okay. When you're talking sidewalks and people and things like that, that doesn't give you much room to swerve.
Yeah, no.
So how does that work?
That's a great point that you bring up, because there's some sidewalks here in Philomath that are only about 3 feet wide. And Dax, I forget the actual width of Dax. I think he's something like 70 centimeters or something like that. Which
2
is
feet by 2 feet.
For
us lay people. Yeah,
right, sorry.
It's not centimeters.
Yeah, it's like I only do stuff in metric with it. But so it's about 2 feet. So you really only got about 12 inches worth of like left-right sway before you're kind of going off the side there. And sure, some sidewalks are wider than that, but you want to design to be able to execute on the the edge case of the narrow sidewalk. And and so you bring up a really important question there, and kind of maybe the first way that we would answer that of saying, if the server is telling us latitude and longitude values, then it would maybe make sense that we should say, well, the robot needs to know its latitude and longitude value. But you sort of hit at kind of the crux of the issue of, you need that latitude and longitude value like really, really precisely.
Super accurate.
Yeah, definitely, because the GPS that's like on your phone, or most GPS antennas or things like that, will give you, your position within about 5 or 6 feet or something like that.
Which works for driving a car.
Oh, yeah.
Sure, yeah.
Well, and I'd say, and the reason why it works for driving a car is because the GPS is relying upon you as a human to know what a road is, and it says if the road is kind of roughly here-ish, you
stay on it.
Yeah. Yes, and then it's allowing all of the like fine correction to be done by you.
Sure, okay.
And so in that case, like 5 feet is perfectly fine. But for a robot where its its ability to do fine correction is not nearly as sophisticated as you as a human, we sort of need to compensate for that lack of fine adjustment, number one, and then number two, the really tight sidewalks, by getting very, very accurate GPS information about where the robot is. And I guess I'm speaking GPS because we're talking about navigating on sidewalks, but in principle there isn't any reason why we couldn't do the same thing inside with fixed base stations around say we're navigating in a hospital or something like that. It wouldn't be GPS per se, but some kind of global positioning system that can tell us, referenced against a known location, where is the robot. And that's kind of what we're doing with GPS, is we're saying, referenced against the known coordinate system of the Earth, where is this robot kind of globally speaking? And it turns out that solving that problem is really hard, because like I was saying, so GPS, it's only really accurate within about 5 feet or so. If you're just sort of, you have your GPS antenna and you're listening for satellites, and you got maybe a fix on 8 or 9 of them or something like that. You're only doing good about 5 feet. And so if you think about that for a minute, you can start asking the question, well, where is the error in that GPS measurement actually coming from? Like what's the pain point in getting a more precise measurement just from a GPS antenna?
Yeah.
And so it turns out that people have been researching this very deeply for like 100 years.
Perfect.
Or sorry, not 100 years. What am I even saying?
Back when Henry Ford.
Yeah, no, I have no idea where that number came from, but it's been going on for a while. I actually don't remember when GPS satellites, I think it was was it the 80s when GPS was first taking off? I don't remember. I need to look that up. But it's been a while that people have been doing stuff.
Greater
with
than our
GPS.
lifetime.
Yeah. Yes. Yeah. Older than me, I'm pretty sure.
Seems like 100 years. Might as well be.
Right. And so you can begin to figure out like what are the major sources of error. And it turns out that the principal source of error in a GPS measurement that you'd like make with a GPS antenna ends up being the atmospheric conditions between you and the various GPS satellites.
Yeah.
So, there's all kinds of like atmospheric things that happen, not just like, clouds and weather and things like that, but, the Earth has, its ionosphere, which is kind of higher up in altitude. I don't remember exactly where the cutoffs are for it, but, the ionosphere has a bunch of charged particles that are sort of hanging out in there, and depending on what's happening from day to day, there's different sort of weather events that actually happen with these charged particles, which introduces both interference into your GPS signal that's actually like going from satellite down to antenna location. And not just interference, it also kind of messes with the wave a little bit in, how long it actually takes for the signal to get to your GPS. And, for people who maybe know a little bit about signal processing, specifically it messes with the phase of the signal that you're getting from the GPS satellite. And so it turns out that that's the majority of the source of error that you get is just basically ionosphere weather is kind of the problem that you have. And so people figured out a pretty clever fix for this, and that is that these kinds of variations in the phase of the signal that you get from these satellites is pretty similar for areas on the globe that are very close to each other. So if I'm doing a measurement from here versus 200 feet that way, the weather that those two signals are experiencing as they get to the GPS antenna are very similar to one another.
Yeah.
And so what you can do is you can say, well, I've got one GPS antenna that is kind of roving around out in my city that I want to know its location very precisely.
Yeah.
But what I can do is I can say, well, let me just like get a second GPS antenna and like bolt it to the roof of my building so that it doesn't go anywhere.
Yeah.
And then I'll just leave that GPS running for days and days and days. And that antenna, I know relative to the ground, it's not actually moving anywhere.
Yeah.
But as I measure its location from, minute to minute and day to day, it's going to slowly drift around in where it measures itself to be.
Oh, yeah.
As the kind of the weather events are changing around it.
Yep.
And so what you can do is you can say, well, if I just basically average the position of the measured position of that fixed antenna over a long period of time, I can sort of average out the effects of weather sort of in this long-term sense.
Yeah.
And I can figure out the true location, the true latitude and longitude value of that antenna very, very precisely just by kind of, averaging a ton of measurements from day to day.
Yeah.
And then once I've done that, I now know I know the true location of this GPS antenna. And so then on a future day, what I could do is I could say, well, I can measure the location of the antenna now. And so I have got the measured position and I know where it should be, and I can figure out basically what the offset between those two is. And I'm sort of going over a few details here, but roughly it is like if you then take that correction between the today measurement and the long-term average, and you can then apply that to your roving GPS antenna. So, the robot that's actually moving around, you measure its location and then sort of undo that correction. And then you can figure out, again, up to the accuracy of your fixed antenna, the actual location of the antenna with the robot.
So what is that accuracy? Like, how accurate are we talking?
Right, and so this is sort of, it depends a little bit on how you apply the correction, and I don't think we should get into that hardly at all. But it can be done in a way that you can end up with centimeter or millimeter accuracy for it, which
That's
is
insane.
Yeah, like absolutely wild. It's, like 2 orders of magnitude smaller uncertainty in your measured location.
That's insane, because satellites, I mean, I'm guessing the GPS satellites are probably in the same range, but it's roughly like 22,000 miles away from the Earth.
Yeah, something like that.
Something like that, yeah.
Yeah, and they're traveling
give or take a centimeter.
Yeah, right. and they're in orbit, right? So they're traveling at high speed.
Yeah.
And so it's this absolutely wild, like you are basically measuring the positions of satellites within millimeters of accuracy, from the ground. So it's
so magic.
Yes, so this is what I'm saying. It's like it is math, it is engineering, but really it's actually magic that's happening underneath the hood.
So if a millimeter is tiny and a centimeter is also tiny.
Yes.
So that's a very precise measurement.
For reference, for people who don't know the conversion in their head, there's about 25 millimeters in an inch.
Okay.
And so then about 2.5 centimeters in an inch. So if you got your knuckle, it's like 5% of the width of one of your knuckles or something like that. So it's pretty tiny.
That's pretty tiny. Mm-hmm. Yeah. Okay. So what happens if I don't know what would cause this? Some major event that you don't have accuracy from either one of those, fixed points on Earth, or satellites get blown out of the sky or something, right? What happens when a robot kind of knows where it is and then it doesn't?
Yes, yeah, well, and I'd say it doesn't even need to be anything nearly as catastrophic as that.
Oh, okay.
GPS works by getting signals from satellites, right?
Yeah.
And so if your robot happens to drive underneath a tree, then it has...
Okay.
Yeah, it can't see the satellites anymore,
right.
And so then your signal goes out. And so, if your robot's just driving down the sidewalk and it goes underneath a tree, there's a short period of time when it's underneath that tree that it doesn't actually have good GPS information coming into it. And, and there's a little bit that GPS chips do these days to kind of basically make inferences about how fast you were moving just a moment ago to kind of guess where you're going to be in a moment and things like that. But typically the way that the chips do that behavior is not nearly good enough to kind of maintain that millimeter accuracy, over the course of navigation. And so basically what you need to do is find some way of maintaining that very precise measurement, even when you're, you have to maintain very precise knowledge about the state of the robot, even when the measurements of the robot's position are temporarily unavailable.
Okay.
So there's a little bit of a difference right there, where there's the actual measurement of the robot's position, and then there is your knowledge about the state of the robot.
Yeah. What do you mean by state?
Yeah. So this would be in robotics. It gets the more technical term would be the robot's pose. Okay. So this is where the robot is, kind of in 3-dimensional space, plus any if the robot has movable parts. What the configuration of those movable parts is. So like in the case of Dax, that would be where Dax's head is pointed.
Okay.
And then additionally, if there's any orientational information that's important. So like is Dax pointed, north by northeast, or, tilted at 5 degrees, or, kind of things like that. So, so a total pose, so description of the total pose of the robot in this context would be, the global positioning, like latitude, longitude, altitude, plus the global orientation of the robot, so where it's pointed, both in terms of its like bearing, but then also if there's any tilt.
So like if it's going uphill or downhill.
Yes, exactly. And then additionally, it would be kind of any tilt with the head.
Within the head,
yes.
Right, which is where the GPS is in Dax.
Yeah, so the GPS antenna is actually mounted in top of the robot.
Smokes.
So, okay, there's a whole other thing which I don't think we have time to get into, but that is, given that you measure because really when you're measuring GPS, you're measuring the location of the GPS's antenna.
Right.
And so if the antenna is on the top of the robot, but that's not, the head of the robot is not really the relevant thing for positioning. What's relevant is where the robot's tracks are. Right. And so you also need to be able to okay, how do I turn that into information about the tracks locations and stuff? And that's a whole other thing, but I don't think we have time to talk about that today.
Yeah.
But to maybe keep our eye on the ball. The thing that's really relevant for navigating is assume that's a solved problem, that you can figure out the track's locations from a GPS measurement.
Yep.
So that is the state of the robot, like where the robot is in reality, is not the same thing as where you measure the robot to be at any given time.
Sure, okay. Yeah.
And additionally, the measurements are something that happen periodically. In our case, I think it's every 200 milliseconds if you're in normal operation, that the robot is actually, giving you an update of where it measures itself to be.
And 200 milliseconds for those of us that only have
clocks
and
sorry,
watches.
Yes, it's a fifth of a second. So,
fifth of a second.
Yeah,
okay.
0.2 seconds.
So every second, you get this information like 5 times a second then.
Mm-hmm.
Okay, all right.
Yeah,
Tracking.
roughly. Unless you drive under a tree and then it just doesn't come for 3 seconds or something like that as the robot's driving along the sidewalk.
Yeah.
And so really what you want to do is be able to know the pose of the robot precisely, and you're trying to figure that out given that you're periodically measuring the robot's position.
Yeah.
And so what you can do with this is there's an idea called dead reckoning, which this is in like orienteering and positioning. I think it's originally a nautical term, where it says, I have knowledge about how my craft, or like a boat in the nautical case, but for Dax, it's the actual tracks. Like I have knowledge about how the robot actually instigates movement, it's the tracks that are actually rotating that drive the robot to move in a particular way. And so what I can do with that is I can say, well, if I know how the tracks are moving, like the speed that the tracks are rotating at, because I'm the one who is applying the voltages to the motor, so I can figure that out.
Yeah.
You can actually figure out where you would expect the robot to be in a moment, or kind of more relevant that you'd say, if I know my state of the robot now, I can figure out where the state of my robot should be in X number of seconds later.
Makes sense.
If I know how the tracks are moving.
Yeah.
And so what you can do is you can say, well, let's say that we have a good GPS measurement, and we can figure out the robot's pose. And then the robot drives underneath one of these trees. Mm-hmm. You can say, well, I don't have GPS measurements anymore, but I did have a valid GPS measurement just a moment ago. And I also know how the tracks were moving in the interim.
And I know how they're moving now.
Yes.
Okay. Right.
And so you can basically propagate forward in steps, based off of what the track speeds are. And you can figure out where the robot is now based off of where it was in the past.
Yeah.
And that is essentially the way that you can kind of stitch together and maintain accurate state information about the robot over time, even if your GPS isn't coming in. Or if it doesn't come in for 3 seconds or 10 seconds or something like that, you can still have a good sense of where your robot is based off of how the tracks have moved.
How long can you go, like theoretically versus actually, right? I mean, you could do lots of testing and have some fun with that. But once you have an accurate fixed position, how long theoretically could you go before you would actually need another signal? Or is the state information so accurate from the information you're receiving that you could drive indefinitely in that state? Or
so how do I want to answer that? You're asking a really, really good question, and it's really complicated. I guess what I would say is knowing the robot's state, or in this case pose, is actually not sufficient for being able to successfully, or I guess safely, follow a path or navigate from point A to point B.
For long term.
For
at all.
Any term. Because if I just tell you the robot's here, the immediate follow-up question would be, well, you just told me a little while ago that GPS is only good in 5 feet unless you got these corrections, and then you can get it down to millimeter accuracy or something like that. And so really there's actually this meta question that you need to ask of, I have the robot state, but how precisely do I know the values that comprise that robot state? So I know the robot's latitude and longitude value, but then immediately asterisk with some tolerance, like plus or minus this value. And so what you do in when you're actually doing this kind of like maintaining state information from over time is every time a GPS measurement comes in, you are using that to update your knowledge of the GPS of the robot's pose information. So you're saying like I have this prior estimate of the robot's here, plus or minus, some tolerance around the robot. And then I've measured the robot to be in this location. And then you can kind of correct and update your knowledge of what the robot's pose is and say, oh, hey, the GPS, gave me a more accurate estimate of where my position is. So let me just, kind of tweak things a little bit.
Yeah.
And now I know better where the robot is and what its orientation is.
Yeah.
And then the robot moves forward, the tracks, iterate forward. And then another GPS measurement comes in, and then you can, again, update your information. But between those two GPS measurements, what the process of dead reckoning allows you to do is it says you're not just propagating your position forward, but you're actually also updating the sort of uncertainty that you have about your position forward.
Sure, okay.
So you would say, like, well, I know where I am right now, plus or minus a millimeter. And as I drive forward, I can calculate, I can give you a number for where I expect to be.
Yeah.
But more importantly, I can say, well, now, but it's plus or minus 2 millimeters that are associated with it.
Yeah.
And then as the robot continues to drive forward, it's now that plus or minus 3 millimeters. And so to answer your question of like how long can the robot drive for, really boils down to how precisely do you really need to know the robot's pose to be, to actually be safely navigating on the sidewalk.
Yeah.
Because in principle, there's no reason why you couldn't just have the robot keep driving forever, without a GPS measurement.
Yeah.
It would just mean that your uncertainties about the robot's position grow and grow and grow because, because I would say it's like, we know that the tracks are moving, the left track is moving at 2.65 meters per second and the right track is moving at, I guess 2.6. Yeah, that'd be fast. Sorry. Like 1.65.
Okay.
And the other one would be like, 1.55 meters per second or something like that.
Sure.
And down to 3 significant figures or something like that. But, as the tracks continue to move forward, there's small amounts of error in those measurements and also the way that the tracks actually slip and slide across the ground itself that introduces uncertainty into the system for dead reckoning. And so you're basically accruing uncertainty as you move forward through the process of dead reckoning. And then every time a GPS measurement comes in, you're kind of compensating for that accrued uncertainty to basically trim in your knowledge of where the robot actually is.
Yeah.
And so, with our tests, we tend to find that, if the GPS information is gone for, 3 to 5 seconds, we're able to maintain like more than adequate knowledge about the GPS or about the robot's pose information.
Yeah.
And I'd say, more than accurate is we've still got it within millimeters of positioning for the robot. And, again, and all of that's dependent on how fast it's going, how, much the robot's turning and pieces of information like that. But the point is that as long as you sort of have this periodic check that's coming in, you can kind of indefinitely maintain global positioning for your robot continuously through time.
Yeah.
And then if it goes away, you can just sort of put in some flag into your, navigation system that says, well, okay, if the uncertainties in my position ever get too large, with under some definition of what too large is, we can then say, okay, well, the robot should stop because I don't actually have confidence that the robot is safely on the sidewalk anymore. Or rather, it's if the uncertainties get any larger, it becomes likely that the robot will fall off the side of the sidewalk or, something like that.
So back to the video that I saw that Sean was showing me about. And obviously I understand that the POV, the point of view user interface screen that I was watching is what the quality control operators are seeing, and it's actual real-time data, and you see the invisible rails, which is one of the patents that we have, right? Mm-hmm. So how does that all tie back into the invisible rails system and making sure that he doesn't go off the rails? Right.
Yes.
Yeah. How does that all come together?
Yeah. Make sure Dax doesn't jump the tracks. Right.
Yes.
It's so the idea with the invisible rails is the intuition for it is what we were talking about at the beginning of we sort of have knowledge of where the sidewalks are roughly that we want Dax to navigate on.
Yep.
And so really the problem that the robot needs to solve is given a particular path that I want to follow, how can I actually execute on following that path? And then offloading the notion of like routing and time estimates to the server so that the robot doesn't need to recalculate that every time.
Makes sense.
And that's basically what the invisible rails are, is the invisible rails say, Dax, here are a set of railroad tracks that nobody else can see. They only exist in a database somewhere as a set of latitude and longitude values. Yeah. And now Dax, here are the tracks that we want you to follow. So now go, chug along these tracks.
Yeah.
And the way that this links to what we were just talking about is embedded inside of that information of what the tracks are is it's not just the location or of the line that we want to follow, but actually the tolerance around the line that satisfies safe navigation.
Okay.
So this would be, if it's a 3-foot sidewalk, the invisible rail in this case would be straight down the center of it with 1.5 feet on the right and 1.5 feet on the left.
Right.
Okay. And the idea is that we say, as long as the robot is within inside those tolerances, then the robot is safely navigating.
Sure.
And so, Dax is on the track in that case. And how that connects with our uncertainties is, again, you ask the question of like where the robot is, but the important follow-up is how precisely do you know that information?
Yeah.
And so we could say, well, I calculate the position of the robot to be right in the center of these invisible rails, but if the uncertainty that's associated with that is like, plus or minus 5 feet, like that's not nearly good enough for navigating on the sidewalk. It's, in terms of statistics, you're saying like, well, there's a, whatever percent likelihood, if it's one standard deviation, it's like 33% that he's way outside of the, actually the tracks that we want him to navigate on. And so what the combination of dead reckoning and GPS allows us to do is say, well, we can figure out a uncertainty around Dax, which allows us to say with a specified confidence where the robot actually is. And so we'd say, well, Dax is here, with a standard deviation, some plus or minus around Dax's position, and then we can compare and say, is Dax's whole standard deviation, kind of his positioning, you could think of it like a circle that's kind of around the robot.
Okay.
Is the circle actually within inside the tolerance of the what constitutes the tracks that Dax is navigating on?
Right.
And if the answer is yes, then you're good. You can keep doing your thing.
Sure.
But if the answer is no, if kind of one of those circles clips the edge of that tolerance, then you can say, well, there is a 10% likelihood that Dax is straying outside of his path, and you could either at that point have the robot pause or do some kind of corrective behavior or something like that. But it allows us to basically then start to make statistical statements about how precisely we know Dax's position and that he's actually following the invisible rails that we've set out for him.
Yeah.
And so kind of that's how the pieces all kind of stitch together. And so if you can do this thing of maintain state information about the robot and then also give the robot these invisible rails to follow on, then you can start to basically say things of like, oh, our robot is doing line following, he's following these tracks. And we can even tell you how likely he is that he's in the center of the sidewalk versus the side of the sidewalk and, put percentages on it and that kind of thing. And so we can then begin to engineer our path following software in such a way that it is safe up to an appropriate safety factor, both for the robot and then if there's, any people that he's sharing the sidewalk with, we can do exactly those same things too.
Yeah. Mm-hmm. So part of the thing that is most astounding to me is we just wrote an article for TechCrunch, right? And the first part of the article is essentially talking about how robots have been on factory floors doing even navigation type tasks for the last couple decades, I guess. Not 100 years, but somewhere in there, right?
Right.
So the last couple decades, but that ability to navigate within a building on a predefined path that never changes. Yep. Absolutely never changes. Seems to me a much much simpler problem than, hey, I'm on a sidewalk in the middle of Ohio.
Right.
And
yes.
there happens to be a tree I drive under and a dog in the way. Like that is.
Yeah, no,
because
it's like in a factory setting, like you can paint lines on the floor, and then all of the humans around know, like, oh, hey, there's going to be a robot that drives through this, area. Like maybe I should be careful when I'm crossing it. But yeah, like on a sidewalk, it's there's no dashed yellow line that says this is where the robot's going to be. That's kind of the idea with the invisible rails, is nobody else needs to see them.
Right.
But that does kind of bring the question of then how do we make sure that the robot is not just blindly following these tracks the way that like a train would, but then how do we do things like stop if someone is in the path that Dax is following, or again, like say it's trash day and somebody's put their trash can out on the sidewalk, or someone's parked their car but the bumper's sticking out into the sidewalk a little bit. Like how do you have the robot make intelligent decisions about saying like, well, given the tracks that I'm trying to follow, can I make sure I don't hit the bumper of this car or not run into this person, or better yet, stop and have an interaction with the person on the sidewalk of maybe do a selfie or something like that.
Right.
And where that kind of comes to bear is closer to like what we were talking about at the very beginning, where I was saying Dax takes a photo of the ground and then is able to classify, this is where sidewalk is, this is where grasses or things like that. And so
Yeah.
you can do things by like classifying elements of your environment using neural networks. And so you can basically have one of those classifications running on your robot as Dax is navigating along. And so then if there is something like a car bumper that's in the middle of the tracks, Dax, a distance down the, invisible rails, is going to see, oh, hey, there's a car over there because my neural network tells me that this thing on my image is a car. And so what I'm going to do is I know the invisible tracks that the server gave me, but now I'm going to kind of bring in the tolerance on one side of those tracks to say the server says this is fine, but I'm going to add additional constraint on top of it to say it's not actually safe today to drive on that location, even if on average it's usually safe to drive
Or
there.
is it also, let's say the car bumper situation, it's in the middle of the tracks, and then I know I need to suck in that tolerance. Do I have enough track or enough tolerance on the other side to get around?
Yes, exactly. And because then it's like maybe it gets so small that in terms of the invisible rails that the server says, it's not actually wide enough.
Right.
In which case the robot could alert one of the quality control engineers to say, oh, hey, can we have a human make an evaluation in the moment about whether it's safe for me to, maybe kind of edge into the margin of the road a little bit, first kind of check over my shoulder to make sure there's no cars coming or things like that. But, at least sort of in the near term, we can limit the number of times that quality control engineers are needing to do things like that by doing things like classifying the location of car bumpers and saying, well, if Dax can just fit through by himself, just like go ahead and squeeze through that kind of small tolerance on the side. You just go for it, Dax, if you're able to.
Yeah.
And having that global positioning in the invisible tracks is the way that we sort of do that task. So using neural networks to like classify objects is one way that we can kind of promote the idea of invisible tracks to make it actually safe for real world navigation on sidewalks. And there's sort of other ways that we could solve that task as well. So, we could do basically collision avoidance systems where we're, using Dax's cameras not necessarily to do full classifications of objects, but basically to just say, the same way that our eyes, we have two eyes and we're able to kind of roughly position things in space based off of that. I can say like, oh, I see that there is a Jason who is, about 2 feet in front of me, and it's my depth perception that's kind of giving me that information. Yeah. We can do a similar thing on the robot where we can just say there is a object, 2 feet in front of me, 1 foot off to the right. And you can sort of bring that information to bear as a very sort of like rapid stopgap measure that if, there's a dog that jumps in front of the robot, you can just say, all I care about is that there is an object in front of me. Yeah. I don't need to do a full classification immediately before I can say, oh, pull the brakes, don't hit the dog, Yeah. And so you can do basically multiple of these systems all in parallel where, you have neural networks that are classifying objects to refine the routing of the robot or the path that the robot follows. Yep. And you can have parallel systems that are making sure that the robot doesn't bump into things or hit things that are, very fast transient events like dogs coming in front of the robot or something like that. But that is then beginning to get into the fine adjustment of actually executing on path following, which is, maybe to loop it back in with the intuition that, there's the, you going to the coffee store or going to the coffee shop is you planned your route and then you started walking and then it's this very fast kind of fine correction that's happening as you're actually walking on the sidewalk to dodge things or to loop it in with Google Maps that when you're driving the car, Google Maps is telling you, oh, this is the road that you should be on, but it's up to you to know what lanes mean and how you actually execute turns and don't hit the biker and things like that. And so all of those tasks, then we can just sort of run in parallel with the robot in real time as it's actually executing the task. But all of it comes back to being able to say, well, how do I even begin following the path to begin with? And that's sort of the big thing that Invisible Rails allows us to do is say, Dax, this is the path that we want you to follow. These are the bounds around the path that's safe for you to actually do it. And then we can start stacking systems on top of that say, don't hit dogs, drive around bumpers, interact with humans, maybe pause and be curious about your environment if you have sufficient time on your delivery. And there's all kinds of things that we can layer on top of it. But kind of the bedrock core is, first of all, the robot has to be able to drive from point A to point B. Yeah. And that's sort of what Invisible Rails allows us to do.
That's fantastic. Well, Jonathan, thanks for taking the time with me today. This has been
of course,
a lot
Jason.
of fun. I think I every time I sit down with one of the engineers, I learn so much more about Dax that I didn't even know was possible. So
yeah, definitely. Yeah, I've appreciated getting to chat with you, Jason. Thanks.